Hi everyone, I'm Cristofaro. I'm here with my friend and colleague Niek. We are from Raelize. Today we are here to share some a bit unusual way of exploiting a trusted execution environment, a TE. Namely, in this case, is QSEE from Qualcomm. These are techniques that we may resort to in some specific cases, and we thought it would be interesting to share them with you. And also because they could be, in principle, adapted to other TEs and other software constructs. So we hope you find this interesting, and sit back, relax, and enjoy. Then let's directly dive into the exploitation of QSEE the Raelize way. After a brief overview with an introduction, we are going to discuss a few results of our research, our unexpected cup of QSEE, something we did not expect ourselves in first place. We're going to show how to break into QSEE using a software vulnerability, but also a hardware vulnerability, which is peculiar for this talk. We're going to have a few takeaways, and of course Q&A. You can always reach to us even after this talk. Feel free to reach out on Discord, Twitter, by email. We're always happy to address your questions, of course. It's me and Nick here, as we already touched upon. We are co-founders of Raelize, and we have quite some experience in analyzing security of devices, system on chip in general. What we both like together is to be in between, and at the boundaries between hardware and software, where they actually meet, and we think that there are still angles to be explored and vulnerabilities to be class of vulnerabilities actually to be discussed and uncovered. In general, we like low-level stuff, software and hardware, things like OSs, trusted execution environment, secure boot, fault injection. Let's get started. We like analyzing connected devices. Here you see a few examples. There are routers, but there are also some Wi-Fi extenders and also some other unexpected devices from Aruba. And what do they have in common? Well, basically, they have in common the same SoC, system on chip. They are all Qualcomm IPQ 4018 and 19 based devices. It's a system on chip, which is aimed for networking device, or actually networked device, which is slightly different. It's a quad-core ARM Cortex with A7 generation and instruction architecture, ISA. So there are lots of interfaces available, made available from the SOC, is I2C, JTAG, SPI, and many devices out there use a chip from this family. For example, OpenWRT already supports 34 different products, and we are aware of devices which are not supported by OpenWRT, but still make use of these SoC. So basically, a few of them eventually showed up in our lab. And we got hooked, we got interested, because the security features that you see on the screen are actually quite uncommon for a networked device. You will see that you have a Qualcomm trusted execution environment. There is also support for secure boot, even an hardware crypto engine. And so this actually made that interesting for us. Long story short, we got actually excited and wanted to look a bit deeper into devices based on the SOC. So we have analyzed multiple of these devices. Although we are going to have a few examples here and there, they all apply to the devices we have analyzed. This talk will be mostly about Linksys EA8300, which is all the examples you're going to see are tailored for this target, for this device. But we know ourselves that these attacks can be easily adapted to other devices. So our findings are, we think they are likely applicable to all devices. And there are even a few that may be even surprising. Well, opening device is the first thing that any hardware attacker would do. Really simple and easy, nothing really special. What you see here is the PCB. And you see already a few pins that may be interesting. And in our case, the first thing that you would like always to find is the UART. I mean, this is really basic stuff. It was really easy to check, just an oscilloscope, or just plug some pin and see what happens. And this is actually the log that we got when we got the UART working. And you can see there is the boot log here. And there are a few interesting sections over here that we can already identify. The first one is that the PBL, it stands for primary bootloader. It's basically the ROM code of the SOC. So this is actually what gets the entire boot process started. And you also see that after PBL ends, there is the start of the SBL1, the secondary bootloader, basically. This is verified by the PBL, or it can be verified by the PBL. And at some point, after the SBL1 has been executed, validated, and performed a few initialization of the hardware, including the DDR, then QSEE is ready to be loaded into memory. So, breaking to the bootloader, can you actually stop into this process and try to see something or explore a bit of the attack surface? It's actually pretty simple, meaning that you see that it's U-boot on the screen already. You see the U-boot with the string boot version, and just press any key while the boot counter is going to 0. There is a short time frame which may be disabled in some cases that basically allow you to enter into U-boot. Again, nothing really special here. Also, we find that some useful commands are not stripped from U-boot here. So you will find TFTP put, you will have NAND and go. So you may be able to already easily to load some code in memory and execute in U-boot, in the U-boot context, basically. So basically, it means that we fully control the RE because U-boot is not QSEE. U-boot is actually running on the RE side. We're going to see that in a moment. Let's conclude a few things first. The boot chain that we are discussing, which should be a bit more easily visible now, is quite similar to some old Qualcomm-based phones. You will see that you have the PBL here, the SBL1, which is loaded into SRAM, and then this will also load and initialize and verify, usually QSEE into DDR, and after this step is done, U-boot is actually loaded and started and potentially verified. And then from it's U-boot task to load Linux into the DDR, the kernel, and get it started, and finalizing the usual kernel and user space boot process. We know that Qualcomm TE is loaded and started. We already seen that in the previous screenshot. We know also that secure boot is broken for RE. So basically, if you can break into U-boot, you can always change the code executed from here, which does not mean that you are able to compromise the boot chain, which is verified or can be verified from QSEE. So, for example, when you are booting a mobile phone, and sometimes you are able to, let's say, change the bootloader, what you're changing in this case usually is only the equivalent to U-boot. So you may have the perfect secure boot chain working here while the RE is fully under control of your attacker. And in this case, it's us. So we also, at this point, having access to U-boot, we just dumped the flash. It was pretty easy. First, we got the partition information. And you see that with the SMEM info, we are able to dump the partition table. It's a standard U-boot command. And you're going to see that here QSEE is printed at this offset in the flash, and this is the size. So there is a dedicated partition which is used to store QSEE. It was trivial to use a TFTP server to dump this partition. Just follow this command. We have the server IP set up. We read the NAND somewhere in 0x89000000, and then from there we just output that to the TFTP server. Again, trivial, nothing really special. So basically, this was pretty easy, and we got to have it loaded into IDA. But then it might be interesting to discuss what to look for in general. So of course, there is the RE, which we are in control, and usually there is, apart from the bootloader, there is the Linux kernel, which is privileged. We call that privilege level 1, just to be clear. In ANV8, it would refer to exception level, but we are in ANV7 environments, so let's call about privilege level 1 and privilege level 0. So basically, PL0 is the user space, is not able to issue SMCs, and PL1 is the kernel space with access to privileged instruction like the SMC instruction. On the other side, so when the CPU is executing in secure world, you have a similar separation of privilege here. You have PL1, you have where both the secure monitor and QSEE runs that privilege with. So this is the privilege that you have for QSEE and secure monitor, and also have an equivalent user space for trusted application. So it's pretty simple and it's pretty classical, typical separation of the based on non-trust zone TE. And in general, the way for switching the execution of one CPU, actually one core of the CPU, because the switching is done per core, is issuing an SMC instruction on the kernel side. Basically, this instruction will generate an exception, which will be trapped, which will be handled into QSEE. Actually, will be in the secure monitor, but from a privilege point of view, in this architecture, there is basically no difference. So please allow us the generalization here. So how this is determined, which code is executed? Again, ARMv7 architecture, you have an exception vector at a certain address, which is stored in the vbar register, vector-based address register. And you go to this address, and at an offset of 08, you have the handler or the starting of the handler for the SMC. So when you are reaching an SMC, your hardware will start executing from here, loading this instruction in the program counter, immediately jumping to the software interrupt. So it's the SMC is dealt with as a normal software interrupt. The software interrupt, so this routine which is executed, actually calls the SMC handler. This is what we refer to as the handler that is going to parse your instruction and act upon that. In order to do so, there are a number of services which are defined, and you see already on the screen a table. We are going to see that in a bit more details. And this means that for each of this table, or each of this record in this table, there is an instruction, sorry, a function handler that is going to handle a specific request. So when you're sending an SMC, you can decide to use or to call into any of these handlers, and you will be passing parameters from the RE. What can we recognize in this table? Well, this is the SMC ID. Basically, this number will affect which value you need to put in R0, in the register 0, in order to select which one of these handler you want to call into. So this number determines what you need to put in R0 when you call the SMC instruction. Then you have a name. Well, they were already there. I mean, we didn't name anything. The symbols were basically there, and it was pretty easy to identify the function purpose, at least from the name. And then we have the routine, the function handler, the SMC handler itself, which will be called, will be executed to. The parameters which are passed through the SMC command, they are basically provided to this function call. So this table, which is typical in this case for an ARMv7, say, device where QSEE is available. So this is a QSEE's typical structure. It's very useful for reverse engineering. In your mobile phone for ARMv8, it will be pretty different because the underlying untrusted firmware has undergone significant changes. So how does it work with communicating with QSEE in general? So you have the hardware, the SoC, Qualcomm IPQ 4019, which provides some separation primitives. You need to be able to separate a few things in order to be able to establish the security boundary between the RE and the TE. Well, first you need to be able to separate execution. So you should be able to distinguishing if you are executing TE code from RE code. You should be able to separate memory, such as that the memory of the TE cannot be accessed by the RE. And also trust zone, in addition to these features which should be there for every TE, provides the ability through some identifier on the bus to separate the access and the usage of peripherals and also hardware modules. On this side, you have, again, the RE in general. This is at runtime. And on this side, you have execute in the QSEE. There are a few caveats here. So this word is not always executing, is always executing upon call from the RE. And this helps the software architecture and the hardware are designed and are used in order to establish some security boundaries. The typical one is between the RE and TE, which should be there in order to make sure that, the TE can be actually trusted or at least trustworthy. Then there is another separation which must be between the different TAs. And this is typically available for a normal TE, for a typical TE today, in order to make sure that a trusted application should not be able to compromise another one. And in order to have these security boundary here, also the other one that would allow an escalation of privilege needs to be carefully enforced, which is between QSEE and the trusted application. Of course, this exists at runtime, but it also needs to be securely started. So you need some secure boot process of any kind in order to have a secure TE, or at least a decently secure TE. This should be the cornerstone of every trusted execution environment. Of course, there is a bootloaders which will execute, initialize, load, verify, and initialize the QSEE side, the TE. But of course, once this is done, they will switch to the non-secure execution, and they will start U-boot. So basically, where we broke into is here, and in principle, this boundary should be already preventing us from accessing anything from QSEE memory, code, and also any other peripheral which is assigned to QSEE. So one communication option that you have with this environment is that you are at runtime, and from Linux kernel you issue SMCs. This is one possibility. But if you have enough privileges on the RE side, including the bootloader, you're running SPL1, you can issue the same SMC in order to communicate with QSEE. And basically, this is what we decided to use. It was much more convenient for us to break into U-boot and from there explore the attack surface. So in our research, our vulnerability should be, and in principle are, accessible to the Linux kernel, so they could be exploited. But the way we researched these vulnerabilities from the U-boot. So our approach was the option 2. Because QSEE is already fully initialized before U-boot is started, and we assume that the environment is pretty much the same. And this is usually, let's say, not a safe assumption, but a reasonable assumption. You should check that, of course. And U-boot provides some features where you can use a standalone application. So you can load your code into memory using the TFTP command, and you can just jump into it. So for us, it was quite easy to extend the running U-boot by having the ability to run our arbitrary code. Just compiled, loaded into memory, and using the go command in order to execute our own code. So how does it work from a practical point of view? Well, you can see that our code calls an SMC call. Well, you need to format the arguments properly. You are calling an SMC call. This is the service you are calling, and the commands. And these are the arguments that are passed to the handlers. In this case, you just see the assembly for running this code, and this assembly is also available into the Linux kernel source code, so it's pretty easy to access it. From the other side, you can actually call any of those services, and this is what you see is the reverse engineering. So it's the compilation with IDA of the function tzbsp is service available. So basically, we control all the arguments which are passed. You see arg1, arg2, and arg3, and we are passing them here, arg1, arg2, and arg3. So we can call this function with all the parameters. So from this point on, it becomes the exploration becomes much easier than just escalating to kernel, for example, from the array. This is for another day. So the first thing that we do, we explore the attack surface. We enumerate the SMC and the routines. So we have two ways. we can reverse all of them and count them, or use a function which is called tzbsp service available to recover all the available handlers. And we just iterate over all the services that we're calling and all the commands. So the combination is pretty easy. 64K, 65536, of course. And at the end of these just brute forcing or enumeration, we are able to see that these are the only ones which are supported into this version of QSEE. And the result match with the SMC and the routines that we identified in the binary in the table. So basically, how do you trust what comes from the array? Well, you need to check, but check based on what? So how do you know if the parameters that are passed to the array are actually safe? So the first thing that should be verified and understood is that, for example, there are a few checks in every, or there should be in every, let's say, service here. You see, for example, this is the register, the value that we put in R1. This is the value that we put in register R2, and this is the value we put in register R3 when we issue the SMC. This is also a verification. So if the R3 is less than 8, you just return, just bail out, and nothing happens. There is also something really interesting here to the fact that the pointer is checked, so is ensured through the function tzbsp is and sec range, is ensured to belong to the array memory. So this means that the TE must have some kind of view of what is relevant, of what is for the TE to be protected, sorry, what is secure memory and what is not. So you need to find a way of verifying if the pointer you receive, which is a physical pointer, by the way, because that's the way it must be in this case, this pointer must be verified to belong to non-secure memory. So basically, this function, this check, prevents bouncing pointer that would read or write to secure memory, because in principle, this R2 could point to anywhere. It's just a physical address. So someone on the TE side that is aware of where secure memory is should be in charge to check it. We are going to go a bit deeper into the secure range, just in the checks. Remember that these checks are fundamental in order to establish the security boundary of the TE. So first thing first is that well, do all the CMC and the routines that are received from the array, are they checked? Well, we went through the entire attack surface by analyzing. One of the things that we identified is one function, tzbsp, blow fuses and reset. And this is actually a vulnerability, and this has been assigned the CV that you see on the screen. So what is the vulnerability here? We pass two arguments here, arg1 and arg2, and you see that the function is allowed range is also in charge of understanding if the arg1 that you're using belongs to secure or non-secure memory. So this is the arg1 is checked to belong to range, but R2 is not checked. R2 is also a pointer, or is used as a pointer, because it is dereferenced and one is assigned to that destination. And basically, you can pass any reference, any pointer to secure memory, and the function will happily write 1, 2, or the output of this routine at the address that you provided. So you have a primitive for writing into TE memory. There is another one that we identified, which is pretty similar. Here you will see that there is no check on this value, but the content of some memory at this address is actually stored at the pointer that you passed, which is dereferenced. So again, you can write the content of the memory at 0x580EO to the pointer that you pass. In our case, we analyzed the value. We identified that it was 0787. It really depends on, say, on the device and its configuration. Another interesting vulnerability, another different CV. Again, all four arguments are passed into a function that returns a value based on the argument. So basically, what we are seeing instead is that arg3 then is assigned the return value of this function. Again, there is no check on arg3. Long story short, you can write anywhere in memory the output value, but you can also write anywhere in memory, depending on how you pass the arguments. You can also write 0x7f, ff, ff. There's also another interesting vulnerable function, different CV here, and no check, and there is argument 2 and argument 3 that you see here. They are directly referenced. In this case, you write 0 to any address, which is pretty convenient, and in arg2, you can write the return value of this function. So what do we have? Several SMC handler routines sanitize the arguments insufficiently. So the check that do perform do not prevent of passing arbitrary physical memory pointer, which may then be used for writing not arbitrary values, but some restricted values in general. So in general, we have an unsanitized pointer, so not sufficiently sanitized, which allows us to write to secure memory. Not arbitrary writes, just a few values. So this is pretty limited, but you can write anywhere. We disclosed all the vulnerabilities to Qualcomm. So if you are interested more in the bulletin, here is the link, of course. But is this enough to achieve QSEE code execution? So are we able to write one anywhere and to turn this into code execution? Well, the first thing that we need to understand is how the secure ranges do work. Well, as we mentioned, there is a need of keeping a table. You need to keep a state as a TE in order to distinguish what is secure memory and what is not. There are a few caveats here and there, but you need to keep some tables in memory. And in the case of Qualcomm, the implementation that you're seeing is pretty straightforward. You are seeing that you have a table made of these records, of these entries that you are seeing. This table, or can be more than one, in principle, in this case is only one, configure a secure memory range. So one of these entry basically configure one single contiguous secure memory range. You have an ID for that range, there are flags for that range, and then you have the start and the end. So you can only define a contiguous memory area. But you can have a table of these entries, of these records, so you can also identify scattered memory as a TE memory. So this is, again, not new. This is identical to the Qualcomm MSM 8974 exploitation from Gal Beniamini, pretty awesome post. But this implementation is still like that. So that approach up to this point can be actually used. It's quite similar. So how did we use this? Well, for example, the function checking if buffer is allowed range, is used in order to understand not only if a pointer belongs to the RE, but an entire address range. So you pass a start, an end, or a buffer, and it's checked if this buffer overlaps with secure memory. If the range is not allowed, such as you pass an integer overflow, so an end lower than the start, you just return. So this is actually taken as a wrong and not acceptable answer. Then you also check if the range is actually enabled, and if the flags1 is equal 1 is enabled. But if flags1 is equal to 0, so the bit 1, so the second bit, what you will find is that this will be 0, and so you will actually continue on the loop. So we will not perform the check, but skip to the next entry. So it's interesting that if the range is allowed, so if you are not able to find any range that overlaps, or secure memory range that overlaps with the range that you've passed, then this is allowed. Then the range start end you have passed is accepted as a non-secure, so good to be operated with. So the map that we found out in memory for our device is pretty simple. Then all the secure ranges are defined and they are all enabled. So bit 1 is set. And what you see here in this range, this is actually the QSEE memory map. So if you or memory range. It's a contiguous range. So if you pass a pointer to those functions to write to QSEE memory, the function is allowed range. So the check will say, hey, this is not good because this range is enabled, and it's going to identify the range that you passed as something which is not good enough. So the following ranges, by looking at, let's say, the complementary of this table, are non-secure memory. So we have all these ranges which are RE memory. The rest is basically secure memory or considered as such. Just see the picture here. The entire 32-bit address is covered in this space. So if it's in this table, it's TE. Otherwise, it's actually RE. It's fully partitioned into complementary ranges. So what if the secure range table is stored in writable memory, and indeed it is because it's data? Then if we are able to set the flag 1 bit to 0 for all the entries will be disabled. Because if we're able to write the flag bit to 0 for all the entries, this is what happens here. And we would just set the flag for disabling the entry. So any range will be allowed because all the ranges will be disabled, and these allowed ranges say, hey, I don't have any secure memory range to be compared with, so any buffer will be okay. So you may remember that one of the vulnerabilities that we identify can be used actually to disable a range entry, for example. We can use this vulnerability to write 1 to the flags field very easily, 32-bit, in order to disable the entry. Well, actually, you need to make sure that the value that is being passed contains a value that prevents further writing to BF2. So basically, this function should fail. Is allowed range should fail, or basically this function should just return that it's the allow range should return that it's a good range, basically. So this becomes pretty easy. The function now, its allowed range, will rely on tables which have been modified. The ranges have been disabled, and the function is allowed range will return 1 for any ranges. So all the checks that function will perform are basically bypassed. So any range check requested by an SMC handler routine becomes basically non-functional. All the SMC handler routine accept the arguments that point to QSEE memory. We basically opened this attack surface. So long story short, we were able to achieve QSEE code execution. This is a story for another time with software, but in principle, we created, we created a read and write primitive using multiple SMC end routines. We combined them in order to have arbitrary read and arbitrary write. We then stored our shellcode in non-secure memory at this address. This is a bit different from the typical approach where you try to inject your shellcode in QSEE memory. We don't care, we just store it conveniently in RE memory, because then we can just modify the MMU configuration to enable that range, map that, it's actually already mapped, map the RE range into the TE MMU and clear the XN bit. At this point, we use one of the function in order to trigger execution from this address, and then we are basically executing our arbitrary code. But today, we are going to talk about something else. And in order to do this, I'm going to hand over to Niek. Please, Niek, go ahead.
Thank you, Cristofaro. Hello, everybody. My name is Niek, and I will be giving the rest of the presentation. What if Qualcomm fixed all these vulnerabilities? Well, if the vulnerabilities are fixed, that means that they're not present anymore. And that also means that we cannot exploit them. However, we can do something different. We can actually resort to fault injection. And whenever we talk about fault injection, we talk about introducing faults into a chip in order to alter its intended behavior. And one of the things that can go differently once you introduce those faults is, for example, the following. This little code snippet is used to enable or disable secure boot. So if the secure boot flag is set to 1, the bootloader is authenticated, and otherwise it is not authenticated. So whenever we make a modification to the bootloader, which is, for example, stored in external flash, and secure boot is enabled, then the authentication function will detect this. Now, using fault injection, we can inject a fault at a very specific moment in time in order to change the intended behavior of this conditional statement. And this allows us to bypass the authentication function and execute a modified bootloader. So we are basically modifying the software that the device relies on by exploiting a hardware vulnerability. So in this case, we are going to do electromagnetic fault injection, EMFI. So it works by driving a high voltage through a coil to generate an electromagnetic field. So the entire circuitry is visualized in the picture on this slide. And this electromagnetic field we emit into the chip's surface in order to cause eddy currents within the chip's circuitry. And due to those eddy currents, the transistors will be affected and will actually enter erroneous states. And this is exactly what we use in order to introduce those faults that allow us to modify software. Because you can imagine, if we affect the transistors that are used to implement the processor, it is not guaranteed anymore that the software will be executed as intended. So what tools do we use in order to generate such an electromagnetic field within a chip? Well, we make use of riskier tooling. So, for example, we use the riskier EMFI probe in order to generate the electromagnetic field. We use the riskier spider in order to set the power that is used by this EMFI probe, so it determines the strength of the electromagnetic field. We use an XYZ stage in order to move the EMFI probe across the chip's surface. And we communicate with the device using a standard USB to UART adapter that allows us to communicate with the serial interface of the Linksys modem that we are targeting. All the hardware we control from our workstation, which is in this case an Intel NUC. And interestingly, one of the things we added to the standard setup is that we are able to switch the power supply of the Linksys device using a relay. And basically this allows us to reset the entire device by setting a simple GPIO pin. And this we control from the riskier spider. So this setup enables us to operate the entire setup completely autonomously. And this is important because typically when you're doing fault injection attacks, you want to conduct many experiments which take multiple days. And the least amount of manual intervention that is required, the more easy it is to conduct a lot of experiments. So an actual picture of this setup is shown here. Unfortunately, I don't have any better pictures. That's a note to myself to make better pictures next time. But what you can see here is the EMFI probe, and it's a big black box. Basically, there's circuitry inside there in order to have a high voltage spike being sent through the coil that is shown here. And this is actually the coil here on the bottom that is placed on top of the chip surface in order to emit those eddy currents into the chip circuitry. So this is the setup that we use to inject the glitches that we are talking about in this presentation. So one of the first steps that we like to do is to perform a characterization step in order to test if the chip is actually vulnerable to glitches or not. So this allows us to identify good glitch parameters in a semi-controlled environment because we control the software and we can write this software in a certain way that we can easier deduct certain conclusions from the behavioral changes that we detect. So for example, it also allows us to determine which locations on top of the chip with what type of glitch power are vulnerable to the EM glitches that we are injecting. Now, because we have control over the software, we can simply repeat the target instructions in order to increase the chances for success. And this allows us to make the timing of the glitch less relevant. As you can imagine, if you need to target a conditional statement, you need to inject the glitch exactly when this conditional statement is being executed. But if you have many instructions that are executed consecutively, then you can basically target any of those instructions. So the characterization test program that we used is implemented as a U-boot standalone application, very similar as during the software exploitation. And what it does is it first sets up a trigger. So this is basically a GPIO signal that is set high. Then after this signal is set, we increase a counter using a stream of add instructions. And once these add instructions are done, we set the trigger low and we print out the counter value. And then the idea is that we know exactly where the add instructions are being executed due to the trigger up and down signal that we set around it. And this allows us to inject the glitch exactly when the add instructions are being executed. So this shows that the timing component from the glitch parameters is taken out of the equation. So what do we expect once we are doing this? Well, if we inject a glitch that is not strong enough, then we expect the counter to be the value of 10,000, because that's the amount of add instructions that you execute. In hex, that is 2710. If we glitch too strong, then we expect no output at all. The printing cannot happen, or the device simply resets. When we affect the code in a way that is too much, so for example, we change the add instruction to something completely different, or we affect the processor in a way that it's unable to execute the software correctly, then we anticipate we get various processor exceptions. But whenever we inject a glitch that has exactly the right strength, and also the probe is exactly at the right location, then we expect responses where the counter value is slightly different. Typically what you see is that the counter is slightly lower, but it can also be higher. And whenever this happens and the printing format is exactly as we expected, then we consider those experiments successful. So we started our glitching campaign running many of these experiments where we move the chip across the chips, move the probe across the chip's surface. So the results can be visualized as follows. So on the right side, we see the chip that we are targeting, and on the left side, we see the grid that we used for the experiments. And we plot all the experiments according to their response. So the green experiments are actually the expected responses. So for these responses, we have no behavioral change whatsoever. So these are probably not too interesting, but on the top right, you see that we have red dots. And this means that on those locations with a particular glitch strength, we were able to modify the counter from its expected value. A clear indication that we were able to affect one or more of the add instructions that were being executed. So from that point on, we identified a few vulnerable locations, and we simply decided to fix the probe on one of the red dots, because we determined and we assumed that this location would yield also glitches when we are targeting QSEE. And in the next slide, we will touch upon why we made this conclusion. So we determined that the IPQ40XX chip is vulnerable to EMFI using our test program. And we also determined that modification of software is likely possible. And we anticipate that this is actually caused due to instruction corruption. So we are able to modify the instructions that are being executed. And we make this assumption because this is a typical behavior for ARM-based chips. And from experience, we know that this is likely the case. An important observation to make is that the same processor is being used for executing the U-boot code and the QSEE code. Because the test program is executed in U-boot, but because the hardware is exactly the same for executing the QSEE code, which is running at a completely different privilege, then if you are able to inject a glitch in U-boot, we are also probably able to inject one when QSEE code is being executed. So this vulnerable location should yield faults in both environments. So let's break into QSEE. So the approach, we bypass a secure range check in the SMC handler routine. Approach very similar to the software exploitation, but then we relied on the server vulnerability. Now we don't rely on any software vulnerability. By bypassing this secure range check, we aim to disable a secure range table entry in memory. And this allows us to disable all secure range checks of other SMC handler routines, very similar as before. And then we simply reuse the software exploit to achieve arbitrary code execution within QSEE. So we reuse some of the knowledge that we obtained from the software exploitation. So what are we going to target? Well, we took a SMC handler routine which is not vulnerable to a software vulnerability. So as you can see here, the argument A2 is actually correctly verified to be within memory that should only be accessible to U-boot. So in other words, it is not secure memory that is only accessible to QSEE. So the idea is that we are injecting a glitch when this conditional statement is being executed in order to write 0 to an arbitrary address, because we have control over A2, which is supplied from the U-boot code. And this includes, of course, QSEE memory. And then the idea is that we are going to override the table entry flag field in order to disable a range, very similarly as what we did before with the solver exploitation. So basically the goal here is to modify the if statement. But this is not where it ends, because the code that is actually responsible for verifying the if the pointer that we pass is in QSEE memory or not is fairly complex. And we already looked at this is allowed range function. But if we start thinking with fault injection in mind, we identify that there's multiple locations where we are able to influence this solver in order to make it return 1 instead of 0. And basically that is what we are trying to achieve, is that we want to modify the intended behavior of this function in order to make it return 1 whenever we provide a pointer that actually points to secure memory. So there's actually many vulnerable locations where we can do this under the assumption that we can modify instructions. And we are doing this just from the decompiled code. If we would be looking into the actual assembly instructions when we disassemble the code, it's likely that there's a whole bunch of different locations, many more than we already looked at, where we can actually influence the solver in a way that allows us to bypass the range check. However, from an attacker point of view, we don't really care what we exactly glitch. I mean, if you want to harden this code against fault injection, you might be interested in this. But from an attacker point of view, we just want to bypass the range check. And that's exactly what we started doing. We did not really reverse the solver in any way in order to identify those locations. We simply start hitting the chip at the moment in time QSEE was being executed. So the standalone application that we used in order to perform this attack is as follows. Again, we set a trigger to tell our hardware when QSEE will be executed. Then we issue the SMC call. And as one of the parameters, arguments that we pass to the SMC call is the actual address of the secure range table entry flag field. So if we would be able to write to this field, we would be able to disable the range field. So of course this is not possible because we're not, we cannot write to this address from U-boot directly because it is actually a secure memory range and the MMU prevents us from writing to that particular location. So this is exactly what we want to bypass within the SMC call itself, is to change the intended behavior of the check that prevents us from writing to this address using this SMC call. Once this SMC call returns to U-boot, we set the trigger low, and that gives us the actual attack window during which we know a little bit of U-boot is executed, QSEE is executed, and U-boot is executed again. Then we call the SMC call again, because if we are successful, we would be able to write to this location, and the error that is returned from this SMC call would be different. So this is an indication, a verifier that we were successful. And then we simply print the return values. Now, in order to identify this attack, we actually used an additional identifier. We noticed that on the Linksys device, and this was not the same for all the devices that we looked at, the MMU was actually misconfigured, and that allowed us to read the secure memory from U-boot. So in this case, then this is actually already a vulnerability by itself. We are able to read out this secure memory address from U-boot, and it allows us to determine if this particular memory address is actually written or not due to our attack. So you don't really need this for the actual attack, but it makes it more convenient to have two identifiers to see if the attack was successful or not. So the type of responses that we expect, well, of course, when we inject a glitch that is not strong enough, we expect the following. So the call of the first SMC returns an error. The call of the second SMC returns also an error. And the flag field that we dereference directly from the U-boot code is 2, because that's the value that is set up by the device when the device is initialized. Now, when we inject a glitch exactly at the right moment in time with the right strength, we expect to receive the following. Return value of SMC call 1 is 0, because we influence the conditional check. Return value of the second SMC call is also 0, because the range check now doesn't fail anymore, because we successfully updated the secure range entry. And the flag field of that particular secure range table entry is actually set to 0 because that's what we achieve with a successful attack. Of course, there's many other responses possible, but we disregard them for now. So when we are looking at the timing, we can see the following. We know that we set the trigger up ourselves. We also know that we set the trigger down ourselves. So within this window is the actual attack window. Now, we also know that within this attack window, there's the U-boot being executed, there's the QSEE being executed, and there's the U-boot being executed again. So we know that somewhere within this window, the moment in time is present where we are able to influence, or where we hope to able to influence the conditional statement. So we plan to inject glitches within this entire window because we do not exactly know how large the chunk of U-boot is and how large the chunk of QSEE is. This attack window does not provide this information. So we simply start injecting glitches within this entire window the moment the trigger goes up and the trigger goes down. So after many experiments, which took multiple days, we got the following responses back. So on the axis on the left, we see the glitch power, so the amount of power we provide to the EM5 probe. And on the axis on the bottom, we see the glitch delay. So basically, that is the attack window. So based on the responses of the experiments, we determined that in the beginning, in the attack window, we get a lot of CPU exceptions. And these are thrown actually by U-boot. At the end of the attack window, we also get CPU exceptions, which are actually also thrown by U-boot. So this tells us that our observation that there's a little bit of U-boot, then QSEE, and then there's a little bit of U-boot, is matching with reality. Now, when we looked further at the experiments we got back, we actually noticed that exactly within this window, the successful glitches were also present. So it is shown that at a very specific moment in time, we were able to gain successful glitches within this attack window. So the success rate of our experiment is quite low because we actually span a large area of glitch parameters. So many of the fields are completely green, and at those moments in time, we were not able to influence the chip whatsoever. But if we actually set the glitch delay and the glitch power to that of a successful glitch within the area where we see a lot of successful glitches, we are actually able to achieve a success rate of 5%. In other words, and we think this is much more important than the actual percentage, we are able to bypass a range check every 20 seconds. So how do we achieve QC code execution? Well, whenever we talk about fault injection attacks, we like to use our fault injection fault model. So basically, how this works is that we break down a FI attack in multiple smaller steps or stages. So in this case, we can describe modifying of secure range table entry as follows. So it starts all by the activation. So what kind of tooling or what kind of mechanism do you use in order to inject a particular glitch? And of course, depending on what kind of tooling or method you're using, it determines what type of glitch is injected. And in this case, we use riskier inspector FI tooling in order to inject a electromagnetic glitch. Now, you cannot just inject the glitch and it will work. You need to shape this glitch in a certain way. So depending on the type of glitch you inject, you have different parameters to worry about in order to shape this glitch. So for example, you have location, you have power and timing when you're talking about an EM glitch. And once you shape this glitch in a correct manner, and this will be target dependent, of course, and also dependent on the tooling that you're using, you are able to trigger a hardware vulnerability within the chip. And these type of hardware vulnerabilities, which may be different if you put the probe at a different location, can manifest themselves in different ways within the chip. So in our case, we were targeting software, and we know that often when you start injecting these type of glitches, you're causing instruction corruption. And once we knew we were causing instruction corruption, we started thinking about what can this bring us. So for example, if you are able to corrupt an instruction, you're also able to bypass or to skip an instruction. But we were using this instruction corruption fault in order to bypass one of the secure range checks of a SMC handler routine. And whenever we were able to do this, we were able to actually modify a secure range table entry in order to disable it and actually disable the secure range check for all the SMC handler routines. Then, once we actually disabled the SMC handler routines, we were able to use the exact same software exploit that we used before. Because the approach is exactly the same. All the mechanisms that this exploit relied on are still there. It just needs the secure range check to be ineffective. And that's exactly what we achieved using the fault injection attack. So we were able to actually achieve arbitrary code execution within QSEE in a very similar fashion as using the software exploit. So let's wrap up. The takeaways of this talk. Well, we identified multiple critical vulnerabilities in QSEE for IPQ40XX-based devices. And these were actually trivially fixed by Qualcomm, as it's simply software. You can simply update the software and the vulnerabilities will be fixed. Very similar to vulnerabilities that are found in other major operating systems. So we also identified that the Qualcomm IPQ40XX-based devices, and more specifically the chips that are used to make those devices, are vulnerable to EMF5 forever. Qualcomm simply indicated to us that this vulnerability will not be fixed, as it is not considered a threat for the threat model that was that they came up with for these particular chips. So this means that somebody that has physical access to the device and it is designed around this chip and it implements this version of QSEE, then it basically means that whatever we talked about today can actually be used to gain full device control of the device forever, because the underlying problem, the hardware vulnerability, will not be fixed. So we also shown that targeting code instead of ARM trust zone hardware primitives is quite effective. So others have shown that it's possible to use fault injection in order to change, for example, the NS bit. But we've shown that actually targeting the code itself, and a lot of trusted execution environments will rely on the correct execution of software, is actually very effective and maybe actually much easier than affecting the NS bit itself. And also, very interestingly, we've shown that software exploits, which are actually made in a slightly different context, can be reused very effectively for FI attacks. Or in other words, if you ever obtain an exploit for a vulnerability that is fixed, using fault injection, you can actually re-enable that vulnerability by changing small pieces of the code in order to make the vulnerability present anymore. But of course, this requires physical access in order to inject the glitches that you need in order to do so. So this was it. We have much more details about the research that we talked about on our website, so feel free to go to our blog and read all about it. And if there's any time left, we are available for Q&A. We are available in Discord for the hour after our talk, and feel free to contact us by Twitter or email. Thank you very much.